Students, friends, again we'll continue our discussion on transport phenomena. There are three transport phenomena in gases on the basis of kinetic theory of gases, namely transport of momentum, transport of heat energy, and transport of mass. Yesterday or in earlier video class we have discussed transport of momentum, that is viscosity, that leads to viscosity. Now the transport of energy called as thermal energy here, that gives rise to thermal conductivity. Different layers. Gas has been imagined to be divided into different layers. Different layers of the gas may have different temperatures. Different layers of the gas may have the different temperatures. Molecules of the gas will carry kinetic energy from the region of higher temperature to the region of lower temperature to bring about an equilibrium condition. Please remember, we start this transport phenomena when the gas is in non-equilibrium condition. We have taken the gas or a system of gas in a non-equilibrium condition, and then we study the transport phenomena. As we know, it's a law of nature. Some system which is unsteady, it will tends to or brings to the equilibrium condition. Similar here in gas also the same thing happens. So molecules of the gas will have higher kinetic energy when the temperature of that layer or the region is more or higher. So molecules, they carry the kinetic energy with them from the higher temperature layer to the lower temperature layer. And this transportation or a transfer of energy, kinetic energy of the gases from higher temperature layer to the lower temperature layer is called as transportation of energy, and that gives rise to thermal conductivity. Let us consider fixed mass of a gas, and here already I have drawn the figure. So it is xy plane, x and z plane. Here we assume the gas moves from left to right, that we had yesterday. We have discussed this, and this becomes simpler because on the same basis we are deriving three derivations, so it will be easy to understand this. So OX is the layer here. We have considered a layer AB, and this layer is at a temperature theta. And there will be temperature gradient along OZ, and the temperature gradient is d theta by dz. d theta by dz. Temperature gradually increases with distance, that is along z axis, and this is known as temperature gradient. Yesterday also I mentioned this. When the system of a gas or a gas is in equilibrium condition, all this layer which I have shown here, they will have a constant temperature when the system is in equilibrium condition. But we have taken the case at the beginning. Of course, the system will settle or will bring about its equilibrium condition but it takes certain time from the unsteady state to steady state, and we have to derive this transportation of energy, or we have to study the transportation of thermal energy that gives rise to thermal conductivity. But this theta is the temperature of the layer AB, and d theta by dz is the temperature gradient, and theta varies along OZ. Above this layer AB, we have taken layer EF, and below this layer AB, we have taken layer CD. So the temperature of these layers in equilibrium condition is constant. This layer, EF layer, is at a distance lambda, the mean free path, and it is above the layer AB, and layer CD is at a distance lambda from the layer AB, okay, that is below the layer AB. These layers are chosen at a distance lambda because lambda is the mean free path, and during that distance called as mean free path, molecules which are moving upward or downward here, they will not collide with each other, and therefore we have taken this as a distance lambda mean free path. Now temperature of layer EF, temperature of layer EF is given by this, that is temperature of layer EF is equal to theta, the temperature of the layer AB, plus there is incremental, this is distance lambda, and temperature gradient here d theta by dz. Similarly, the temperature of the layer CD, which is below the layer AB at a distance lambda, temperature of layer say CD, that is say here theta plus lambda, that is minus here, sorry, theta minus lambda d theta by dz. So we got the temperatures of two layers, one which is above the layer AB and one which is below the layer AB. Now this means this layer EF is at higher temperature compared to layer AB and compared to layer CD, and the temperature of the layer CD is at lower temperature. Now naturally the temperature of layer EF continuously goes on decreasing. As a result, the temperature of the layer CD goes on increasing till the equilibrium condition is achieved. Here the number of molecules crossing unit area of layer AB, the number of molecules crossing unit area of layer AB in a downward direction or in the upward direction are equal to number of molecules crossing layer AB in downward or upward, direction will be equal to NC by 6. N, where N is the number of molecules per unit volume N, and C is the average velocity at a given temperature. So if M is the mass of gas molecule, or m is the mass of each gas molecule. There are n number of gas molecules per unit volume. M is the mass of each gas molecule. Then the mass of the gas molecules crossing. See, m is the mass of individual gas molecule. Here, the total mass of the gas molecules crossing either in upward direction or in a downward direction. Total mass of the molecule crossing the unit area of layer AB, or the number of molecules or the mass crossing or flowing or moving through this layer AB either in upward or downward direction is equal to, that is, m is the mass of individual molecule into the number of molecules here, Nc by 6. Nc by 6 is the total mass or mass of the molecules which are crossing, coming downward or going upward, crossing this layer AB. Let say CV. We know this specific heat of the gas at a constant value. Let CV a specific heat of the gas at constant volume. CV is the specific heat of the gas at a constant volume. Then the heat energy carried by the molecules. If CV is the specific heat of the gas molecules at a constant volume, then the heat energy carried by the molecules from layer EF crossing the unit area of AB per second in the downward direction. I'll repeat this. If CV is the specific heat of the gas molecule at a constant volume, then just a minute. If CV is the specific heat of the gas molecules at a constant volume, then the energy carried by the molecules in crossing the unit area of layer AB in downward direction in 1 second is equal to mass of the gas molecules, total mass of the gas molecules coming from the layer EF through this AB towards CD, mass into specific heat of the gas at a constant volume into temperature. I'll write specific heat into temperature. Fine. I'll write this mass. We have got this mass is equal to Nc by 6. That is, Nc by 6 are the molecules which are moving either upward or downward direction. M is the mass of individual molecule. M into Nc by 6 gives the total mass of the molecules which are coming in the downward direction, that is from layer EF to the layer, say crossing the layer AB towards a layer CD into CV, specific heat of a gas at a constant volume, into temperature of this layer, that is theta plus lambda d theta by dz. This is. Similarly, the heat energy carried by the molecules in crossing the layer AB in upward direction. The heat energy carried by the molecules in the layer, or heat energy transferred carried by the molecules from the layer CD through this layer AB per unit area of this layer AB per second in upward direction will be equal to, say, mNc by 6 into CV, here theta minus lambda d theta by dz. This is. Now let us write the net transfer of heat energy per unit area of layer AB in upward or downward direction in 1 second. Net, therefore, net transfer of heat energy per unit area of layer AB either in upward direction or in a downward direction in 1 second. Let me write that amount of heat energy is equal to net amount of heat energy Q is equal to mNc by 6 CV into theta plus lambda d theta by dz minus this mNc by 6 CV theta minus lambda d theta by dz. So after simplification, what we get from this, that is Q, the amount of heat energy will be equal, this is common, mNc by 6 into CV, C suffix CV. So here theta, this becomes minus theta, this becomes lambda, this becomes plus, that is into 2 lambda d theta by dz. This will be equal to this 1 by 3. It is mNc CV upon 3 lambda d theta by dz. I will write this Mn is equal to density, that is amount of heat energy Q is equal to 1/3. Say Mn is rho, the density of the gas, C, the average velocity, lambda, the mean free path, d theta by dz. This is the net amount of heat energy flowing either in a downward or upward direction per unit area of layer AB per second. And this we got it. In this, rho is the density of the gas, C is the average velocity of the gas molecule, lambda the mean free path, and this is temperature gradient. Once we have this, let us go for the basic definition of this. Basic definition of thermal conductivity. And thermal conductivity K, it is denoted by letter K. Thermal conductivity K of the gas molecule is defined as the quantity of heat that flows per unit area per second per unit temperature gradient. So coefficient of thermal conductivity K is defined as the quantity or amount of heat that flows per unit area per second per unit temperature gradient. So Q, the amount of heat energy, by definition this is K, the coefficient of thermal conductivity, d theta by dz, or K is equal to Q, the amount of heat energy flowing per unit area per second, that is d theta by dz. This is definition of thermal conductivity. Once we get this Q, the amount of heat energy by definition, we have calculated net amount of heat energy flowing per unit area of layer AB, either upward or downward direction, that is the net amount of heat energy per unit area of layer AB per second. Once we get this Q can be equate with this Q, so this will be equal to K d theta by dz is equal to 1/3 rho say C, 1/3 rho C, here it is CV also into lambda, 1/3 rho C lambda say CV d theta by dz. This is, and this we get cancel, so K, the thermal conductivity, coefficient of thermal conductivity, K is given by 1/3 rho C average velocity lambda into specific heat of the gas, and this is the expression for thermal conductivity. Once we understand a concept here on the basis of transport of phenomena, we had yesterday derived the coefficient of viscosity. Same treatment here, same thing. Some of the things we have combined here. You will go through my notes which I have uploaded. Please go through, read the notes, watch the video, and keep yourself busy in this difficult time. Don't spend your time. Time is very precious. So also life is very precious. Time is also very precious. So don't waste your time in doing some other things, though there is no guarantee or something, we are not sure whether the university will conduct the examination or not, but as for the knowledge sake, you should prepare this, you should read this, try to understand the concept. One or other day this will help you. Well, this is the expression for thermal conductivity. Let us derive relation between, I'll rub this now, a simple derivation, relation between thermal conductivity and say coefficient of viscosity. Relation between say eta and K. I have given this. So eta is the coefficient of viscosity, that is eta is equal to 1/3 rho density of the gas, C the average velocity, and lambda is the mean free path. And below this K is given just now, we have obtained K is equal to 1/3 rho C lambda into CV, specific heat. So if you look at this, the K will be equal to K, the thermal conductivity, is equal to, this is 1/3 lambda, 1/3 rho C lambda, 1/3 rho C lambda. This is equal to eta into CV. Is the relation between coefficient of viscosity and thermal conductivity. Look, this is simple. We got it theoretically, but this expression for coefficient of thermal or the relation between two doesn't holds good experimentally, and people have done some correction to it, and therefore K the coefficient of thermal conductivity is given by this epsilon eta into CV, where eta is some factor, eta is equal to say 149, this gamma, that is specific heat ratio, minus 5, specific heat ratio, that is Cp by Cv. So using this K, it is 1/3 say epsilon rho C average velocity C lambda into Cv. This is corrected value or expression for thermal conductivity using this. So we have written the relation between K and eta, that is thermal conductivity and coefficient of viscosity. Once we got this, let us go for temperature, effect of temperature on conductivity. Effect of temperature on conductivity. Let me write it here. Say effect of temperature on conductivity. Okay, the conductivity I have written in short. Well, we know this K WKT, I will write here KT. We know K, the thermal conductivity, is given by the expression epsilon eta CV. Right? One expression, and see this K is also given by this, that is 1/3 rho C lambda into Cv. So this is rho is the density. I will write this as 1/3 mn C lambda. Let me write Cv first. Cv into lambda, and this will be equal to 1/3 mn C Cv. Lambda is 1 or root 2, that is Maxwell's expression, 1 or root 2 pi sigma square into n, where sigma is the diameter of the molecule. Already we have obtained this. So this n and this n gets cancelled. So the K, the thermal conductivity, is equal to m mass of the molecule, C the velocity, average velocity, Cv specific heat, divided by 3 root 2 say pi sigma square. Look at this. K, the thermal conductivity, is directly proportional to say average velocity. Therefore, we write this C or Cv, they are directly proportional to square root of absolute temperature. We know that C is directly proportional to absolute temperature. Therefore, K is directly proportional to absolute temperature. Coefficient of thermal conductivity of a gas is directly proportional to the square root of absolute temperature. Hence, the coefficient of thermal conductivity K increases as the temperature goes on, that is absolute temperature goes on increasing. Let us discuss the effect on K, effect say of pressure on K, the thermal conductivity. Yesterday also we have discussed the effect of temperature on coefficient of viscosity and pressure, effect of pressure on coefficient of thermal conductivity. Here, let me write this now. That is, K is equal to, say, epsilon eta CV. Eta is the coefficient of viscosity. If you look at this, epsilon, eta and CV are the parameters, and these parameters are independent of pressure. Eta, say epsilon, eta and CV are independent of pressure. Independent of pressure. Therefore, coefficient of thermal conductivity K is also independent of pressure. Say pressure P. Okay. This is how these two vary with each other.